Okay, let's keep going. Okay. Now, we have explained that last hour we spend some time explaining how to make a general, a flexible, and reasonable assumption for the relationship of the cost and effect of marketing instrument, right? Okay, and we say that we can actually, with a simple lines of code, okay, we can make a general, a reasonable, and also flexible cost-effect function, right? To basically simulate any kind of marketing instrument. Okay, that's what we go, and we can say that the parameter MBA would actually reflect to the maximum effect, the medium cost, and actually the effective range of cost, right? That's the and now with this assumption, we are going to estimate the expected payoff, right? Okay, okay. So if we know the MBA and we know the X, right? Which means that we know the MBA. I say that this thing should be written by the function of incremented purchase probability of X, right? It's the delta P function delta P of X given MBA, right? As I say that. So when we have the MBA, we know the characteristic of this instrument. Then we need to determine the X, right? And when we have the X, we have the delta P. And we know the delta P, we can calculate with this logic, right? We can actually calculate the payoff, right? For every customer, right? Okay. So now this is the code. Okay. So basically the expression should be like this one, right? For every customer, we already know their expected revenue, right? So if I increase their buying probability by delta P, the revenue will be increased by delta P multiplied by M, right? Okay? So this is the expected increment of revenue. Okay? After we apply the instrument, right? Delta P, this is the increment of probability, right? And the M is actually the expected revenue that we already have predicted, okay? And then this incremented revenue have to multiply by margin to get the incremented profit, right? And the incremented profit need to deduct it by the cost, right? To get the net effect of this instrument to every one of the customer, right? Okay, but this thing has a condition, right? It only apply for P plus. P is actually the expected probability, right? And delta P is the effect that we apply instrument P. If that is more than 1, it will become unreasonable, right? Because buying probability cannot be higher than 1, right? For example, if a person and his P is already like 95%, and delta P is like 10%, right? And that in that case, because the P is already like 95, right? So the increment will have to be calculated by the probability increment has to be calculated by 1 minus P, right? Because the maximum probability is kept at 1, right? So we need to have when we calculate the net effect, we need to take this into consideration. That's why we have two cases here, right? Okay. The mathematical things is written like quite complicated, but actually when we written in code, it was just like one line. It was just like 2 lines of code, okay? So so in order to do that simulation in the example, this is what we do, okay? Now, first of all, we need to have this margin, right? So if we do a calculation from the real data, you will find that the margin is like just only about 17%. But this is very unreasonable in retailing. If your raw margin was just like 17%, this retailer would not survive, okay? So somehow I think in our assumption we can raise the in your final examination, I would suggest you to raise the margin to like maybe 40% or like 50%, right? So otherwise you will not see the reasonable number, okay? So but however, this is just for illustration. Explanation purpose, let's say that the margin is like 17%. Okay, now we can set the MBA to like 0.2, 25, and 40. Okay, and we set X to 30. Okay, so in order to calculate delta P, we basically follow this equation, right? The delta P is either 1 minus B, right? In our example, if some person, the delta B can be determined by calling the function directly, right? If we know M, B, A, and X, then delta B can be calculated directly by calling this function that we defined it here, right? Okay. So delta P itself is actually quite straightforward. The reason that we want to put this is because that some customer already have a very high probability. For example, you already have a probability of like 95%, right? So if the delta P is like 10%, then its buying probability would like be 1.05, which is not a probability at all, right? Probability cannot exceed 1, right? So we need to choose the minimum of these two expressions, right? That is why we call P minimum, right? So with that, we already calculate the delta P, and then you know the delta P, you time it by the expected revenue, time it by margin, and minus the cost. It is the ER, right? Okay? So because we are doing in R, right? So this is the vector of length like 2A531, right? That's actually do this, okay? This code chunk, and then we go to here. We assume the margin is 70%, and here we set the value of MBA and X, right? So MBA and X, we set the value. And then here, we can calculate the delta P. As you can see that this delta P is a vector of 2A531, right? Because the delta P can be different from customer to customer. Most of the customer will have a effect of 15.5, but some customer will not have a delta P of 15.5%. For those people whose expected probability is already like 90%, the delta P would be only 10%, right? Right? So the delta P can be different from customer to customer. And also that when we do this REV. In this column actually is the expected buying revenue for each of the customer, right? For all of the customer. So when we do this, we actually also have an ER, which is expected return for this 2A531, right? Okay. So for each one of our customer, we actually simply by using this 2 lines of code, we can calculate their delta P, right? Given MBAX, and then we can calculate their net expected return. Okay, and every customer will have a different net expected return, as you can see here, right? So we basically can do a histogram, right? Expected return. You can see that. For actually, if we have a instrument like this one, if we only have a margin of like 17%, then most of the customer will have a negative net expected payoff, right? Okay, only this customer that has the expected net effect more than 0 will produce a positive effect if we apply this instrument to this customer, right? So this is very, very important concept here that I want to express. In modern business analytics, the reason that we want to do modern business analytics, because we can use model to predict each customer's behavior, so that when we choose the customer, we can apply the instrument to only those customers who have a positive expected payoff, right? If I can choose customer, for example, if I have an APP, if I use my APP to distribute, to send out my cash coupon, right? For these people, I would not send this coupon, right? Because they are actually have negative expected payoff, right? I would only send coupon to those who has the positive expected payoff, isn't it? Right? Okay. So with this delta B and expected return vector, right, we can actually answer the following question. Right? The first question is how many customers have the positive expected payoff, right? And that is very easy, right? See, we just do a logical expression to test ER. ER is a vector of 2A531, right? And how many of them have ER larger than 0? We can use sum to calculate the positive case, right? So how many of them? Only 6, 7, 9 customers out of this 2A531 has the positive expected payoff. Okay? So if we apply this instrument to every customer, which means that for all of these 2A531 customers, if we apply this instrument to them, right, what is the total expected payoff? It's very easy, right? Just sum it up. Okay? So you can see that we will have minus 202,000. Okay? We will lose money. If we have an instrument like this one specified by this MBAX and our margin is like 17%, then if we apply this instrument to every customer, actually we will lose 200,000. Okay? So we will not do that. So what if we only apply those to those who have positive expected payoff, right? So we use this ER larger than 0 to do a conditional index. Still remember the conditional index, right? Okay. So we choose only those who has ER larger than 0 and use that as index to this 2A531 vector, right? and we sum up those who only have positive expected payoff, then as you can see that if we apply to all customers, we will lose 200,000. But if we only apply to this 667 out of the 28531 customer, we will earn 80,000, right? It's a big difference, isn't it? Right? That's why you need to do that's why we want to do the business analytics, isn't it? Right? That is the reason that we want to do the business analytics. Okay? Now let's move on. So if for some reason we want to apply the instrument to those who have expected payoff larger than 10, and it is easy, right? We just change this index, right? So you see that if we apply to those who have expected payoff larger than 10, we actually would earn 33,000. Okay, because you are now applying to less people, right? And your budget is lower, right? Why we want to do that? When we can earn 80,000, why we just want to earn 63,000? Well, maybe you do not have enough of budget, right, to apply to all of the people, right? So you can actually you only want to apply to customer who has the higher expected payoff, right? Okay, and following this logic, you can actually like select whatever customer you want, right? Specify the condition here, right? And simulate. If we apply to those who live in Z115, sorry, it should be Z115, and then have expected larger than 10, right? Just write the condition here. Use that condition as the index to index this ER. Then you basically can simulate when you apply that instrument to any specific group of customers. Okay? That is the basic thing that we do the simulation in R. Okay? So in R, actually make the assumption and simulation very, very simple, right? For assumption, we basically just use one line of code. Okay? Just one line of code. We can make an assumption that specifies the cost effectiveness relationship between any marketing instrument, right? And that assumption is so general, so flexible that all of the market instruments can be represented by adjusting X, M, B, and A, right? Okay. So with that assumption, we can calculate the delta P, and then with delta P, we can calculate the expected R. And in order to do these two things, we basically need to use the prediction, right? And in this B data frame, we already have the prediction for this 28531 customers already, right? So in that case, actually, we can like, right? We basically can do the simulation in just like 2 lines of code, right? So just one line of code is for assumption, 2 lines of code for simulation. Okay, so all of the complexity in this slide and also in this slide, it's all of the complexity in these 2 slides in our environment. Okay, you can actually like implement in just 3 lines of code, right? Okay, So, so it's very easy, isn't it? Right? Any question up to this point of time? Okay? So if you know how to do it, right, it's easy to write a program. Okay? Okay? Just, so any question about this 3 line of code and about the explanation we do so far? We have basically already go through this maybe I should track it here so it's easier. We already go through this assumption and simulation. As I say, the assumption was just 1 line of code, right? The simulation for one given instrument, okay, just one given instrument, it's just 2 lines of code, okay? So it's not that complicated as you thought, okay? Let's say we would, because we, up to this point of time, we basically fix the value of x, m, b, and a, right? But in the real situation, when we know m, b, a, we need to optimize x, right? Okay? X is the thing. That we say that MBA is the characteristic of a marking instrument, okay? And X is the strategic parameter that we can determine, right? Okay? The reason that we assume that this MBA, basically, if you can, in enough time to do some marketing survey, you can actually determine what the MBA is, okay, for an instrument to a certain group of people, right? You can actually do that, okay? But here we do not have time to cover that, so we just do it by assumption, right? So assume you know that MBA, you need to determine X for the beta effect, right? Isn't it? That is the second thing we want to do, right? We want to maximize X given MBA. Say it again. We want to maximum X given MBA so that we can maximum the total net expected payoff, right? Okay. So, and how to do that? Again, we can do the simulation here, right? It's marketing simulation. Now, look at this line of code. The difference between this line of code and this line of code is that now here we assume X as a single value, right? Okay, it's a fixed value, just cash coupon and $30, right? Now, if this cash coupon, we actually can change its face value, right? So we want to do a simulation on a cash coupon starting from $10 to $45. Okay, so so if we want to do that, we need to set the capital X as a vector of cost coupon of the cost coupon, right? So let's go back to here. So after I do this line of code, I will have an X vector, right? From 10, 11, 12, 13, from 10 to 45. We want to do the simulation here, right? We simply use the sapply function code, and then basically the simulation code is exactly the same. Just here, now we want to apply X. X is this vector, right? The first time I use X10, and then the second time I use like 11, 12, 13, right? Okay, so with that, in this sapply function code, I would like apply all of the X in this sequence to this function. And with that, I can calculate for each x the expected return for applying this instrument to all customer, and then applying the number of customer who has n is the number of customer who has positive expected revenue, and then e return 2 is actually when I apply this to only those who has positive payoff, right? This is applied to all customer. This is applying to only those who are positive. Okay, so for each of x, I can calculate all of this number and make it into a data frame. So when I execute this, I will see a data frame that for each of the different x, right, the coupon value, I can see that they are different, right? I see that the expected payoff when I apply to all of the customer. And this is the number of customer who has positive expected return. And this is when I apply to those people who has positive return, right? And if we plot this data frame in ggplot, we basically would see something like this, right? This is the expected return. When we apply it to all of the customer, you can see that it's all underwater, right? So the x is actually the value, right? The value of the cost coupon, okay? And this curve is actually how the expected total expected payoff vary with x, right? As you can see that we cannot apply this tool to all of the customer because no matter what x it is, it's always under water, right? And this is e return 2, right? Which means that when we apply to only those who has the positive expected return, then we would earn about, when we change x, right? When x is too small, actually we do not have profit. But when we set the x to this value, it's about like $35, right? We can have a maximum, as you can see here, when we set that, when we set x to 34, we actually can apply to 700 people, and we will earn 98,000. Okay, so actually, given MBA, we can, given the if this is a cash coupon, right? We can set the value of cash coupon at $34, right? And this is the optimum X value, okay? And in that, we will find 7,000 people to apply this tool. And in that setting, we can have the, okay? We can have this E return 2, we can earn this much money, okay? So in this simulation, we push one step forward, right? Knowing this MBA, we can determine the optimum X that lead to the maximum expected payoff. Any question about this logic? I'm sorry, I need to run for the washroom for a while. So let's take a break now, and then I think I'll be back in like 10 minutes, okay? So we won't take any more break after that, okay? Sorry about that, just